The grand Riemann hypothesis is an extension of the original Riemann hypothesis to a broader class of functions, known as L functions. The original Riemann hypothesis, proposed by Bernhard Riemann in 1859, is a conjecture about the zeros of the Riemann zeta function, which is a function that plays a key role in number theory, particularly in the distribution of prime numbers. The Riemann hypothesis states that all non-trivial zeros of the Riemann zeta function lie on the critical line in the complex plane, which is the line with real part 12. The grand Riemann hypothesis extends this conjecture to all L functions. L functions are a general class of complex functions that include the Riemann zeta function as a special case. They are associated with various types of mathematical objects, such as number fields, elliptic curves, and modular forms. Each L function has a critical line in the complex plane, analogous to the critical line of the Riemann zeta function. The grand Riemann hypothesis states that all non-trivial zeros of these L functions lie on their respective critical lines. In other words, it conjectures a precise location for the zeros of all L functions, just as the original Riemann hypothesis does for the zeros of the Riemann zeta function. The grand Riemann hypothesis has deep connections with many other conjectures and theorems in number theory and algebraic geometry. Here are a few examples. 1. Generalized Riemann hypothesis GRH. This is an intermediate step between the RH and the GRH. It extends the RH to Dirichlet L functions, which are associated with Dirichlet characters. The GRH further extends this to all L functions. 2. Artin's conjecture. This conjecture, proposed by Émile Artin, concerns the L functions associated with Artin representations of Galois groups. The GRH implies a special case of Artin's conjecture. 3. Birch and Swinnerton-Dyer conjecture. This conjecture is about the L functions associated with elliptic curves. The GRH would provide important information about the order of the zeros of these L functions at the central point, which is a key part of the Birch and Swinnerton-Dyer conjecture. 4. Langland's program. This is a vast web of conjectures and theorems that link different areas of mathematics. The L functions that appear in the GRH also play a central role in the Langland's program. 5. Weil conjectures. These conjectures, which have been proven, are about the zeta functions of algebraic varieties over finite fields. These zeta functions are closely analogous to the L functions in the GRH, and the proof of the Weil conjectures has inspired many of the techniques used to study L functions. 6. Prime number theorem and its generalizations. The RH gives a precise error term for the prime number theorem, which describes the distribution of prime numbers. The GRH would give similar results for generalizations of the prime number theorem to other arithmetic progressions and number fields. These are just a few examples of the connections between the GRH and other areas of mathematics. The GRH is a central conjecture that touches on many different fields and problems, and progress on the GRH would likely lead to progress on many other conjectures and problems as well. F1 geometry, or geometry over the field with one element, is a relatively new and abstract area of mathematics that has been developed to understand and generalize patterns and structures that appear across different areas of mathematics. The connection between the grand Riemann hypothesis, GRH, and F1 geometry is not direct, but rather through the broader landscape of number theory and algebraic geometry. The GRH is a conjecture about the zeros of L functions, which are complex functions that encode deep arithmetic information about various mathematical objects. F1 geometry, on the other hand, is a framework that aims to unify various phenomena in algebraic geometry and number theory. One of the motivations behind F1 geometry is the idea of functoriality, which is a key part of the Langland's program, a vast web of conjectures and theorems that link number theory and representation theory. The Langland's program, in turn, has deep connections with the GRH. For example, The Langlands program predicts the existence of certain L functions and gives a conjectural description of their properties, which includes the statement of the GRH for these L functions. While F1 geometry and the GRH are both part of the rich tapestry of modern number theory and algebraic geometry, they are on different threads. There has not been a direct application of F1 geometry to the proof of the GRH. However, the development of new mathematical frameworks like F1 geometry often leads to unexpected breakthroughs and connections. So it's possible that future developments in F1 geometry could have implications for the GRH. The grand Riemann hypothesis, if proven, would have far-reaching implications in number theory and related fields. It would provide a deep understanding of the zeros of all L functions, which would in turn shed light on the mathematical objects associated with these functions. For example, it could lead to breakthroughs in understanding the distribution of prime numbers, the behavior of number fields, and the properties of elliptic curves and modular forms. Despite its importance, however, the grand Riemann hypothesis remains unproven, and proving it is considered one of the greatest challenges in modern mathematics.